a molecule like buta-1,3-diene is said to have conjugated double bonds because the two bonds are separated by another bond, in this case a single bond. So conjugated double bonds generally are double bond, single bond, double bond. Okay? A conjugated diene, like buta-1,3-diene, is electron rich, much like the previous alkenes we've studied in this chapter. So it can undergo electrophilic addition with a Bronsted-Lowry acid like HCl. Notice, though, that we end up with two products here. These are isomeric products. One product, 3-chlorobute-1ene, really appears to be as expected, right? Because the H and the Cl have added across one of the double bonds with Markovnikov's regiochemistry. So this is really what we would predict. And notice this is symmetrical, right? So this is what we would predict. The other product, though, that 1-chlorobutene, can't be produced simply by the addition of the HCl across a double bond, right? And notice the double bond now is in a different place, right, than the starting material. So, of course, we get to investigate as scientists why. Now, first, we need to analyze the products just a little bit. The HCl the hydrogen and chlorine atoms that added to the diene to produce 3-chlorobute-1ene are separated by 2 carbon atoms, making it the product of a 1,2 addition. So the 3-chlorobute-1ene is called a 1,2 addition. Now, where those numbers come from is no matter where the conjugated double bonds are, they're numbered like 1, 2, 3, 4. Okay, so even if you've got like a really big molecule, right, and you have like conjugated double bonds here and here, you still get some sort of numbering like 1, 2, 3, 4. So the idea here is that the 3-chlorobute-1ene is called the 1,2 addition product because it adds across the 1,2 bond. Okay. The other product is called the 1,4 addition product. So this is the 1,4 addition, right? And the hydrogen and the chlorine are added to the diene, are separated by 4 carbons here. And we're going to see in the mechanism why this is called the 1,4. But basically, the hydrogen adds to the 1 chlorine, and then, the 1 carbon, and then the chlorine adds to the 4 carbon, okay? And that's why it's a 1,4 addition. The buta-1,3-diene that's shown here, just as an interesting aside, is a precursor to polybutadiene, which is a synthetic rubber that's used to manufacture tires. This can also be converted into dipenitrile, which is a precursor in the manufacturing of nylon 6,6 synthetic fibers that are found in swimwear and carpets and parachutes and many other products. And my hope is that we'll get to, if we have enough time, we'll be able to synthesize nylon in this semester. So that's one of the precursors to nylon. Now, both reactions are produced from the same general mechanism. And so I want to show you this mechanism. So let's start with our friendly, just one of the simplest conjugated double bonds we can have. So this is buta-1,3-diene, and it's going to go through an electrophilic addition with HCl, okay? And so this is nothing out of the ordinary. These electrons come here, and those electrons go there. Now, there's going to be some resonance, so I'm going to build a big bracket there, a big bracket. Now, when we look at this, right, and think about how things are added, the first kind of thing that we think about is, okay, hey, look, that double bond's going to stay the same. This is going to come down. That's going to go up. The hydrogen has added to the first carbon here, but we're not showing it. But we can also have a resonant structure here where, and I'm going to show you this in blue, so this is not part of the mechanism, it's just the resonant structure. These electrons can flip here. When those electrons flip, for lack of a better term, we know they're not really flipping, or they're really distributed, right? You get that resonant structure, okay? So these are in brackets, these are the resonant structures. Now, chlorine here can add to either one of these. So one chlorine molecule comes up and adds right there to that guy, and then another chlorine molecule comes up and adds right there to that guy, right, through coordination reactions. And when we've added through these coordination reactions, that's how we get the two products. So we end up with, as one of our products, right, that's 3-chlorobutene, that's the 1,2 addition product, and then we also end up with the 1,4 addition product, right, which is 1-chlorobutene. So this is how we get these products. Both products are produced from the same carbocation intermediate. So we get both of these. Now, addition of the proton on the first step of the mechanism occurs to give the more stable carbocation intermediate, okay? So notice on this very first addition, right, it's going to follow Markovnikov's rule, where there are 2 hydrogens here and only 1 hydrogen here, so the other hydrogen is going to go here, right? It's not, the hydrogen's not going to add here because this is too unstable, okay? So, but in the previous mechanism, the carbocation intermediate, right, that's produced by the addition of the H plus to the terminal carbon is resonance stabilized. And so that's why it goes on to form the 1,2 and the 1,4 adduct. If one of the internal carbons were to gain the H plus instead, then the positive charge in the resulting carbocation would be localized. So I want you to notice here that another reason this is really unstable is there is no resonance, because that makes those electrons localized there. There can't be any resonant structures. So by having the positive charge be on this carbon, that opens the door for resonant structures, and so that's one of the reasons it's so stable. Now, electrophilic addition of butyl-1,3-diene produces a mixture of addition products, right? We get the 1,2 adduct and the 1,4 adduct from the same carbocation intermediate. But I'm sure the burning question in your heart is, which adduct is the major product? Well, to answer that, we really need to look at the temperature, okay? And so we can use the temperature to control which product we're going to get. It's a major factor in electrophilic addition reactions because the temperature of the reaction governs whether the reaction is reversible or irreversible. So, at high temperatures, which is typically, when we talk about high temperatures for us, that's room temperature or above, okay? So if we're running this reaction at room temperature above, electrophilic addition to conjugated dienes is reversible. And it takes place under thermodynamic control. So the major product is the one that's the lowest in energy, right? The major product is the one that's the lowest in energy. At low temperatures, and this is typically well below room temperature, electrophilic addition to a conjugated diene is irreversible, right? And takes place under kinetic control. And so under kinetic control, the major product is the one that's produced the fastest, okay? So we can use temperature to either get the thermodynamic product, the one that's the lowest in energy, or the major product, the one that's produced the most rapidly. One of the things that you're shown here as well is the reaction coordinate diagram. What we can see here is high temperatures give the products enough energy to cross over the energy barrier in the reverse direction to reform the reactants. So at low temperatures, the products have insufficient energy to overcome this energy barrier, right? And so that's why we say at low temperature, they're irreversible. There's not enough energy to go backwards. But if we can increase the temperature, increase the energy by increasing the temperature, then we can go backwards here. And so that's why one's reversible and one is irreversible, and it's temperature dependent. Now, the thermodynamic product of the electrophilic addition to a conjugate diene is generally the one in which the remaining carbon-carbon bond is on the most highly alkyl substituted double bond, okay? So it can be either the 1,2 or the 1,4 adduct. So the thermodynamic product right, is generally the adduct with the remaining carbon-carbon bond, right, that is the most highly alkyl substituted. So this can either be a 1,2 adduct or the 1,4 adduct. And I want to remind you about being alkyl substituted. And what we're talking about there, right, is the number of R groups. So for example, if I have this guy with 3 R groups, and I have this guy with 4 R groups, this one is more highly substituted. So in this instance, that would be the thermodynamic product. So if we look over here, this is the 1,2 adduct, right? It's added here, but we come here and we look at this double bond. And on this double bond right here, there is only 1 R group. So when we look at this, it's like saying, hey, look, there's the R group, and they're hydrogens. So we only have 1 R group stabilizing that. When we come and look at the 1,4 adduct, right, there are 2 R groups. So there it is. And then you've got 1 R group here, and then you have a hydrogen. And then you have 1 R group here, and then you have a hydrogen. And so because there are 2 R groups around that double bond, that one becomes the one that's the more highly stabilized. Okay, so when we're talking about the most highly alkyl substituted, that's what we're talking about with a thermodynamic product. When the reaction is carried out at room temperature under thermodynamic control, right, we see here that the 1,4 product of this reaction tends to be the major product, right? It's the most highly substituted. You still get a mixture, but that's the major product at room temperature. So it's the 1,4 adduct there because we have 2 R groups versus 1 R group around the double bond. Now, if we do the same reaction at low temperatures, right, what you're going to see here, this is under kinetic control, is the 1,2 adduct is the major product, right? So that's the major product. What we find is that the 1,2 adduct is always going to be the kinetic product. So the 1,2 adduct, I've typed it out for you. The 1,2 adduct is the kinetic product because of the location of where the reaction occurs. Basically, the Cl, right, when these electrons come here and drag back that proton, the chlorine is just closer to that partial positive charge than the one for the resonant structure. So this is just formed faster, right? So the kind of nice thing here is that the 1,2 is always going to be the kinetic product. And then you have to evaluate what's going to be the thermodynamic product based on the number of R groups. So the thermodynamic product can either be 1,2 or 1,4, but 1,2 is always going to be the kinetic product.